Okay, so we are now at this theorem. So you know how to find eigenvectors, you know how to find eigenvalues. Next thing is going to be what leads us to be able to perform diagonalization. So first property that we must see is that the union of linearly independent families of eigenvectors associated to distinct eigenvalues is linearly independent. So what do we mean here? The following thing. Assume you have three eigenvalues, lambda 1, lambda 2, lambda 3, okay, which are distinct, okay? You've got your matrix. I don't speak about any size of the matrix. It could be any size, but let's say you have three distinct eigenvalues, so it must be at least of dimension 3. Yeah, you understand. Otherwise, I wouldn't never be able to have three eigenvalues, three distinct eigenvalues with a 2-2 matrix. Anyway, so let's assume that they're all different from each other, and let's denote v1, v2, v3, three eigenvectors associated to this eigenvalue. So actually, the proof of that property would be an induction. So we're going to show it for 2 and 3, and then, well, if you want to do a rigorous proof, it should be an induction, a rigorous induction. But, well, let's say we don't have time for this now, and you can find this in many books, and we will talk about this later on also. Okay, so first we will prove that V1 and V2 are linearly independent. Okay, how can I prove that? Well, assume they are not, and let's prove that you get some incongruity. Uh, so by contradiction, okay, that's the proof we want to make. Okay, so assume V2 is K times V1. Okay, they are not linearly independent. When I've got two vectors, it means that they are collinear. So what do we have? We have that A times V2, well, it's just going to be A times K times V1, which is K, A, V1. And as we said, A is V1 is an eigenvector associated to lambda 1, so that's just going to be K lambda 1 V1, and I can also write this as lambda 1 K V1. Okay, and so that's exactly going to be equal to lambda 1 V2 by the assumption that we said. All right, and okay, yep, and but on the other hand, I've got that V2 is an eigenvector associated to lambda 2, so it should be equal to lambda 2 times V2. So what do I get? Only possibility for, well, I've got this equality, and what does it mean? It means that lambda 2 minus lambda 1 times v2 is equal to 0, and as we assume that v2 was different from 0 because it is an eigenvector, we get a contradiction, right? Because it would imply that lambda 1 is equal to lambda 2, which is a contradiction. Okay, so two eigenvectors associated to two different eigenvalues can't be collinear, right? Now let's see if I add a third one, right? Can we have that V1, V2, V3 linearly independent? Okay, all right, and you see that you could actually do the global reasoning would be assuming that if you've got n eigenvalues and n eigenvectors associated to different eigenvalues, then assuming that at rank n minus 1 you've got n minus 1 linearly independent vectors, what's happening if you add another eigenvector coming from a different eigenvalue? Okay, so that's the reasoning. What we're going to try is the same thing by contradiction. We're going to assume that we have, so we should take other letter than lambda, so let's take alpha. Assume that we've got alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 is equal to 0. Okay, so what comes next is a very common techniques. I think you should be able to reproduce this proof. All right. So this is our assumption, and we want to prove that. Well, the only way that the following reasoning is going to be true is that if a1, alpha1, alpha2, and alpha3 are 0. So let's apply a to that whole equality on both sides. Okay, so on one side I've got a times 0, so that's just going to be 0. On this side, I've got a times alpha1 v1 plus alpha2 v2 plus alpha3 v3. Okay, so that's going to make alpha1 a v1 plus alpha2 a v2 plus alpha3 a v3 should be equal to 0. As they are all eigenvalues, I get that this is alpha1 lambda 1 v1 plus alpha2 lambda 2 v2 plus alpha3 lambda 3 v3, and that should be equal to 0. Okay, let me rewrite that one here. Okay, and actually I'm going to rewrite it and multiply by the eigenvalue lambda 3, assuming it's different from 0. Okay. Um, Okay, if it's equal to 0, actually you have that the previous equality here would be 0, and then you get that alpha1 and alpha2 would already be equal to 0, and that if you go back to the first equation, that one here, you get that the only possibility is alpha3 is equal to 0. So if lambda 3 is equal to 0, it's already proved. Now let's assume that lambda 3 is different from 0, and we get so alpha 1 lambda 3 v1 plus alpha 2 lambda 3 v2 plus alpha 3 lambda 3 v3 equal to 0. So let me say it again. I have multiplied this line by lambda 3, and that gives me this one. All right? So now I've got my two lines, and I'm going to subtract one from another. What's going to happen? Those terms are going to cancel. That's what I'm doing it for, actually. All right? So, and then I get alpha 1 times lambda 1 minus lambda 3 v1 plus alpha 2 lambda 2 minus lambda 3 v2 is equal to 0. And what can we use? We can use the fact that we proved earlier that v1 and v2 were linearly independent. Okay? Why is that helping me? Because this is exactly a linear independence formula that I have here. We know that all the lambdas, the lambda 1, 2, and 3 are all different 2 by 2, okay? So lambda 1 minus lambda 3 v1 or lambda 2 minus lambda 3 v2 are different from 0. And this linear combination is equal to 0, and I know that my vectors are independent. So that implies that alpha 1 is equal to alpha 2 is equal to 0. All right, and if I've got alpha 1 is equal to alpha 2 is equal to 0, that means here this cancels, and we're left with that one here. And as v3 is different from 0, it implies that alpha 3 also is equal to 0. Okay, so right, so it would be nice if you would be able to reproduce that kind of proof. All right, but the very important lesson from this, and if you have more than 3 eigenvalues, 3 eigenvectors, you can do an induction, a correcting induction. Okay, but the important lesson is that you can build a linearly independent family of vectors using the eigenvectors, right? And the important thing, the important corollary to this property, maybe we should write it explicitly. If we have, so assume we are still in Rn, n distinct eigenvalues, then we will have n linearly independent vectors, eigenvectors, and so I will have a basis of Rn. You see that I'm going slowly towards my change of basis formula, okay? The p dp minus 1 that we stated first, actually, okay? So keep that in mind. This is going to work because for each single eigenvalue, I can associate an eigenvector, and if I've got n, let's say if I'm in R3, my matrix is 3, 3, and I've got 3 different eigenvalues, then I know that I'm going to have 3 different eigenvectors, and that these are going to make a basis of R3. Okay, so what is written next in that theorem? So in dimension n, there are at most n eigenvalues, so we've already said that, because anyway, it comes from counting their multiplicity, it comes from the characteristic equation, but we get that result again because we know that we won't be able to have linearly independent family with more than n vectors. Okay. The thing is that we have the next inequality. The dimension of the eigenspace associated to an eigenvalue is at, at least 1, because we can't have an eigenvalue without having an eigenvector. But the question is, if I have multiple eigenvalues, do I have as many corresponding eigenvectors? Okay, so let me take a counterexample for this one. You remember we had some matrix looking like this, okay? And we make the determinant and we get 3 minus lambda, 2 minus lambda, okay? So eigenvalues are 3 and 2, and we had found 2 eigenvectors, 2 eigenvectors, okay, independent. So they are linearly independent. All right. Now let me show you a very, very similar matrix. Let's take 3, 3, 1, 0. Okay, this one. Instead of a 2 at the bottom, I've written a 3. Determinant of this one. That's just going to be 3 minus lambda square. Oh, determinant of this minus lambda. Okay. All right. The characteristic equation is going to be 3 minus lambda square. What does it tell me? It tells me that 3 is a double root. Okay, so 3 of the characteristic equation, right? So 3 is a double eigenvalue. An eigenvalue of multiplicity 3, of multiplicity is 2, sorry. Okay, so the multiplicity of 3 is 2. Okay, problem here. If I'm looking for the corresponding eigenspace, what should I solve? I should solve a minus 3i. So that's going to be 0, 1, 0, 0. Okay, times xy is equal to 0. And what do I get? I get only one condition, that y should be equal to 0. Okay, and so my eigenspace associated to 1 is going to be spanned by one single eigenvector, the one where x is free and y has to be equal to 0. Okay, I only have one vector. All right, and I don't have enough to build and one eigenvalue of multiplicity 2 and one eigenvector in R2. I don't have enough eigenvectors in order to build a new basis of R2. Right, so that's going to be a problem. But we could see that if ever well, we'll talk about this later. Okay, so well, what I wanted to say is that if ever it were diagonalizable, you already know that the formula would be something like this. And if it were diagonalizable and we've got the eigenvalues on the diagonal matrix, that would be similar to the 3 times the identity. And so if you've got p and p minus 1 on the sides, that's just going to collapse into some identity, 3 times identity. And obviously this is my original matrix was different than 3 times identity. Okay, so that's all completely logical, of course, consistent. All right, so let's come finally to our main theorem and our most important thing. A is diagonalizable if adding the basis of all eigenspaces, we obtain a basis of Rn, okay? And in that basis, A is represented by a diagonal matrix, and we can even precise with eigenvalues on the diagonal. And hence the formula for A and P, the change of basis matrix. The change of basis matrix are going to have the eigenvectors in columns, the corresponding eigenvectors on the same column as with the same order as the eigenvalues in the diagonal matrix. And this is our big formula, okay? A is equal to P d P minus 1. Okay, so let's read that small note before we do an example in the next video. To sum up, we need n linearly independent eigenvectors in order to diagonalize R, because we want to make a basis of Rn in order to obtain a matrix P that is going to be square and invertible, right? And so, therefore, if A has exactly n distinct eigenvalues, only single roots to the characteristic equation, A is diagonalizable. And if A has multiple roots, well, it's going to depend whether we can find sufficiently enough independent eigenvectors for multiple eigenvalues. Okay, so here you are. You have almost, well, all the theory we need for the moment. Next video is going to be an example, and then we will see some applications.